On paper, the question had already been answered. Every major science outlet agreed on a number: the mass of the heaviest object the human species had ever catalogued, the structure that surpassed every previous benchmark in the known universe. That number was 100 billion solar masses. Then the James Webb Space Telescope observed that same object for 12 hours, continuously, using the most sensitive infrared spectrometer ever built. The paper it produced was published in Nature on February 5, 2025. The mass figure in that paper was 10 billion solar masses. That is a factor of 10 between the headline and the measurement. No official statement from NASA, Chandra, or the James Webb Space Telescope team has been issued to account for the difference. This is a story about what that silence means. The object at the center of that silence was first detected in 2010 by the South Pole Telescope, a faint Sunyaev-Zeldovich signal in the southern sky flagged in a wide-field microwave survey, catalogued under the designation SPT-CLJ2344-4243. Over the next 2 years, follow-up observations using 10 independent observatories began to reveal what was actually there. Michael McDonald, then a postdoctoral researcher at MIT's Kavli Institute for Astrophysics and Space Research, led the investigation. His first encounter with the cluster had come through the Magellan Telescope, an unexpected hazy circle of blue light at the center of the image. In mature galaxy clusters, central galaxies glow red. Old stars, cooling slowly, producing nothing new. The blue meant star formation, the kind of furious, sustained stellar birth that should have ended billions of years earlier. McDonald, describing the moment the scale of the discovery became clear, said, "We really didn't realize how remarkable it was until late last year and early this year, when we got follow-up X-ray and optical and ultraviolet and infrared measurements that constrained the star formation rate." The cluster was named Phoenix for the southern constellation, and for a mythological parallel that turned out to be precise. Its central galaxy had been dormant for billions of years, a dead structure in a dying system. It had come back to life. The August 15, 2012 Nature announcement confirmed what that return looked like at scale. Phoenix's central galaxy was producing approximately 740 solar masses of new stars every year. The Milky Way produces between 1 and 2. Phoenix's central galaxy contained roughly 3 trillion stars, compared to approximately 200 billion in the Milky Way. The cluster was also the most powerful X-ray emitter of any known galaxy cluster in the observable universe. In 2012 press coverage, Phoenix A's central black hole was placed at approximately 10 billion solar masses, described at the time as the low-end estimate. The cluster's total mass, including dark matter, hot gas, and all stellar content combined, reached approximately 2.5 quadrillion times the mass of the Sun, placing it among the most massive gravitationally bound structures in the known universe. The recognized comparison point for black hole mass at that time was a quasar first catalogued in 1957 on photographic plates at the Tonantzintla Observatory in Puebla, Mexico. Astronomers Braulio Iriarte and Enrique Chavira had recorded a faint blue-violet point of light and given it an entry number, TON618. Its nature as a hyperluminous quasar, an active galactic nucleus powered by one of the most massive compact objects in the observable universe, was confirmed in 1970 by a radio survey conducted in Bologna, Italy. The mass of its central black hole was measured in 2004 by Ohad Shemer and co-authors, publishing in the Astrophysical Journal, using the H-beta emission line to track gas orbiting at 10,500 kilometers per second. The result was at least 66 billion solar masses. Sagittarius. A star, the black hole at the center of the Milky Way, has a mass of 4 million solar masses. Torn 618 is 15,300 times heavier. Its event horizon, the boundary beyond which nothing escapes, including light traveling at 300,000 kilometers per second, spans 1,300 astronomical units. That is more than 40 times the distance from the Sun to Neptune, compressed inside the gravitational boundary of a single object. If Phoenix A's black hole genuinely reaches the theoretical 100 billion solar masses, its event horizon would extend 4,000 astronomical units, a boundary so vast that light, traveling at 300,000 kilometers per second, would take 71 days to complete a single orbit of its outer edge. TON 6118 sits 10.4 billion light-years from Earth, which means the light arriving now left it approximately 3.4 billion years after the Big Bang. The universe was still assembling its first major structures. TON 6118 was already this. In September 2015, Brockamp and colleagues uploaded a paper to Arxiv, a theoretical modeling study of the Phoenix cluster's gravitational dynamics using n-body simulations. Their estimate for the central black hole's mass was on the order of 10 to the 11th power solar masses. That is 100 billion. The paper was not a direct measurement. It was a simulation derived from indirect gravitational modeling. Popular science adopted the estimate, circulated it as established fact, and began describing 100 billion solar masses as Phoenix A's confirmed mass, without flagging that no instrument had ever returned that number from direct observation. The James Webb Space Telescope was designed precisely to resolve this kind of uncertainty. In July 2023, it turned its instruments toward the Phoenix cluster. The number it returned was not the one the headlines had been printing. The James Webb Space Telescope study was led by Michael Reif, a physics graduate student at the Massachusetts Institute of Technology's Kavli Institute for Astrophysics and Space Research, working under McDonald. Published in Nature on February 5, 2025, the paper carried the title Directly Imaging the Cooling Flow in the Phoenix Cluster. Its scientific subject was the intermediate temperature gas at approximately 300,000 Kelvin, the thermal link between the cluster's superhot plasma and the cold filaments where stars actually form. Webb detected this gas distributed in clumps and filaments across the entire field of view, a three-dimensional thermal map of a star-forming system in real time. Reif described what the observation had revealed. For the first time, we have a complete picture of the hot to warm to cold phase in star formation, which has really never been observed in any galaxy. The paper described Phoenix A's central black hole as roughly 10 billion solar masses. The most sensitive infrared spectrometer in history had observed Phoenix A for 12 continuous hours. It returned 10 billion. The split between official scientific literature and popular science on this specific object now runs across 3 instruments, 13 years of data, and a factor of 10. McDonald's 2012 Nature announcement reported approximately 10 billion solar masses, described as the low-end estimate. The 2019 follow-up study from McDonald's group using Chandra and Hubble found 5.8 billion solar masses in cool gas filaments. Reif and McDonald's 2025 James Webb Space Telescope. Nature paper reported roughly 10 billion solar masses. The Brockamp 2015 Arxiv theoretical model returned 100 billion solar masses. 3 direct observational papers spanning Chandra, Hubble, and the James Webb Space Telescope return a consistent range of 5.8 to 10 billion solar masses. 1 indirect simulation returns 100 billion. Space.com in December 2024 described Phoenix A as having an estimated mass of 100 billion suns. No NASA press release addressed why that figure is a factor of 10 larger than every peer-reviewed study produced by the researchers who actually pointed instruments at the object. Chandra's archive contains no correction. The James Webb Space Telescope team's 2025 paper was published, covered widely, and prompted no official comment connecting its 10 billion figure to the number that contradicts it. The word tension does not appear in any official communication about Phoenix A's mass. Neither does discrepancy. That is not an oversight. It is a decade of institutional silence on a specific, verifiable question about the universe's most extreme known object. McDonald, in the coverage of the 2025 James Webb Space Telescope paper, offered one question about the Phoenix system. The question now is, why this system? The question applied to the star formation mechanism. The gap between 10 billion and 100 billion solar masses, the question of which number reflects reality, was not addressed. Priyamvada Natarajan, professor of astronomy and physics at Yale University, whose work on black hole growth limits earned a Time 100 designation in 2024, has established a theoretical framework for how large a black hole can grow before the universe itself prevents further accumulation. Her team's framework places a physical ceiling at approximately 100 billion solar masses. Above this threshold, the feedback mechanisms that drove Phoenix A's extraordinary star formation, radiation pressure from accreting material, high-energy jets disrupting in falling gas, and tidal forces clearing the black hole's food supply, become actively suppressive. Growth does not slow, it stops. If the Brockamp theoretical estimate is correct, and Phoenix A's black hole genuinely reaches 100 billion solar masses, it sits at Natarajan's ceiling. The universe built the largest object its own physics permits. The James Webb Space Telescope pointed at that same object for 12 continuous hours and returned 1/10 that value. Two answers exist for one object. Neither is the one popular science has been presenting as confirmed. If the peer-reviewed observational record is accurate, if Phoenix A weighs approximately 10 billion solar masses, then TEON 6018 at 66 billion is more than 6 times larger. Popular science has been circulating the wrong number about the universe's most extreme known candidate for over a decade. The correction was available in McDonald's original 2012 paper. Martin Rees, Astronomer Royal and Emeritus Professor of Cosmology and Astrophysics at the University of Cambridge, commented on the Phoenix Cluster announcement at publication. This spectacular starburst is a very significant discovery because it suggests we have to rethink how the massive galaxies in the centers of clusters grow. He identified the need to rethink. Nobody rethought the mass number. Bradford Benson, an astrophysicist at the University of Chicago, involved in the original 2012 Phoenix Cluster analysis, offered a warning at the same announcement. The galaxy and its black hole are undergoing unsustainable growth. This growth spurt can't last longer than about 100 million years. The growth stopped. The discrepancy did not. If the Brockamp theoretical estimate proves correct, if a future instrument designed specifically to probe Phoenix A's gravitational dynamics through direct stellar kinematics or gas dynamics confirms 100 billion solar masses, then the universe has reached one of its structural limits and we have already been looking at it. That would mean the most energetic object the cosmos can build has been in our catalog since 2012. The James Webb Space Telescope returned 10 billion from the same object. The uncertainty does not resolve cleanly in either direction, and the reason it does not connects to a breakdown that extends well beyond Phoenix A. The Hubble tension, the persistent, statistically significant disagreement between the two independent methods for measuring the universe's expansion rate, now confirmed beyond 7 sigma, draws on the same cosmological standard model that generated Brockamp's 100 billion figure. The equations governing expansion rates also describe dark matter clustering, galaxy formation at cluster cores, and black hole accretion across cosmic time. A black hole mass derived from n-body modeling. Inside a framework that cannot reconcile its own core measurement is not a confirmed result. It is a projection carrying unknown systematic error from the broken model it was built on. As of May 2026, no peer-reviewed study has been designed specifically to resolve the 10 billion versus 100 billion discrepancy through direct observation of Phoenix A's gravitational field. The Vera Rubin Observatory's ongoing wide field survey may eventually constrain cluster masses at this scale. The European Space Agency's LISA mission, when operational, will detect gravitational waves from merging ultramassive black holes, providing indirect population constraints on objects in this size range. Until those results arrive, 3 instruments, Chandra, Hubble, and the James Webb Space Telescope, confirm Phoenix A at 5.8 to 10 billion solar masses. One simulation says 100 billion. McDonald's 2012 Nature study, the 2019 Chandra and Hubble follow-up, and Reef's 2025 James Webb report all return a consistent range of 5.8 to 10 billion solar masses across 13 years of direct observation. Natarajan sets the theoretical ceiling at 100 billion. Popular science placed Phoenix A at that ceiling. Official science has not confirmed it, corrected it, or explained the gap. That is two incompatible stories about the same object, running simultaneously inside the same scientific community. The same physics that cannot reconcile those two numbers is the physics that governs what is reachable, what is buildable, and what the universe ultimately permits. If that physics is complete, then the limits it describes are real, and we are already living at one of them. If it is not, then so are the possibilities that lie beyond what it can currently see. What would you need to see before you knew which version of the universe you're standing in?